Okay, so hello everyone. Hi, welcome. Let's see. Yeah, welcome back. I hope you all had a good weekend. So welcome to the last lecture of the course. I mean, it's been a weird term for sure. I have a few announcements that I think I would normally do at the end of the lecture, but I think a lot of students are watching the recorded lecture, so I'll do the announcements first, so that everybody sees them. So first of all, there was a request on. Well, okay, there were several requests on Piazza for an extension to the assignment 5 deadline. And so, if you don't look at Piazza, do have a look at Piazza for the details of the extension. I try to balance, I want to be fair to students who have been working hard already and have, finished assignment 5 or are almost finished by the original deadline. But on the other hand, I have some flexibility for a short extension, and hopefully, even if you are finished, you'll be able to use a little bit of extra time for some extra testing. So the code is extended until Sunday, so by 4 days. But the document, make sure to get the assignment 5 document submitted by the original deadline, which is this Wednesday, which is in 2 days, right? So it's very soon. And so the code is due on Sunday, and I'll use that code for the secret tests as well. So you have until Sunday to, fine tune and test and get your code really good for the assignment 5 test, but also for the secret tests. And then the other announcement is the course evaluations. There's a deadline for those of Wednesday as well. So if you haven't completed the course evaluations, please do that, so I get your feedback to improve the course for the future, and so that the university, they use those to evaluate instructors and to choose, who gets to teach what next time, and so on. Okay, so we just have, let's see, some more things to finish up, right? So last week I talked about generating better code. And so I specifically looked at instruction selection. And for a CISC processor like x86, we have these crazy, these big instructions that do a lot of things all in one instruction, like this one. And so, we wanted to find ways to actually generate those complicated instructions. And so we were doing this tree tiling algorithm, where we first created a more detailed AST that exposes all the actual low-level operations that you want to implement. And then, for each instruction, we had these tiles, these little pieces of an AST that instruction implements, including, where's my, okay, and I guess I erased the really complicated tiles. So here's a tile that's a little bit more complicated than the other ones. And so the idea is that some of these tiles actually have multiple AST nodes, and a single tile can implement multiple nodes of the AST. And then I, waved my hands and covered the AST with some tiles, in this case, these 4. And then we just sort of did the whole tree traversal code generation, but traversing the tree of tiles, I guess this tree down here, the tree of tiles rather than the AST, right? So we had that last time. And so the only thing that's left in this algorithm is, how do you do the part where I waved my hands and I found a good tiling? And I already said that we assign a cost to each tile. So in this case, it was based on the number of instructions in that tile. And so we want an algorithm that is going to cover the AST with tiles while minimizing the total cost of all the tiles, the sum of the costs of the tiles. So let's look at how we can do that. All right. So the tiling algorithm and sort of the algorithm. The one word summary of the algorithm is you do dynamic programming on the tree, kind of going from the bottom up on the tree nodes. Right. So our input is an AST. We'll call it T. And for the output, well, we're going to output two arrays. I'm going to output min cost of n and a tile of n. So these are two arrays indexed by a node of the AST n. And I need lots of space here. All right, let's erase more stuff. Okay, so here the min cost, well, it's going to be the minimum cost of tiling the subtree rooted at n. And then tile of n is going to be the tile that I should place on n to achieve this minimal cost. Right? So tile to use at n to achieve that cost. Okay, so basically I'm gonna traverse the tree kind of from the bottom up or in a depth first search order. So for each node n in a depth first search order. Okay, and so the order is important because I want to process all of the nodes below a given node, before I process that node first. So, for example, if the minimum cost for this node is going to depend on the minimum costs of nodes that are below it in the tree, but are processing in a depth first search order. So I'm going to cover the nodes below a node before I come back to that that node. I guess I should I should really say a post order, right? So I not just depth first search. Let's say depth first search post order. So I visit a node after I've visited all its children. Okay, and so I'm at a node, let's say this one here. And at this point, I'm going to look at all my tiles. So for each tile T that matches that node. So that matches n. All right, and I mean, I'm waving my hands a little bit about what it means to match a node, right? But the tiles are these little pieces of a subtree, so they have to have the same shape as the node and the subtree below it. So for to match, say, this example node, it could be matched by that tile that I just had right over here that matches that node plus its various children beneath it. But this node could also be matched by a single tile that is just the dereference operator, right? So any tile that matches that node and sort of its immediate vicinity, depending on the size of that tile, right? I could overlay the tile over the tree starting at that node. Okay, if that's not clear, do ask questions. But I mean, that's as precisely as I'm going to define the whole idea of matching, right? Basically, I want to look at all the tiles that I could possibly use for this particular node. And then for each of these tiles, I'm going to compute a tile cost. Okay, and this is where the DP is going to come in. So the cost of using a particular tile T is going to be, well, first of all, the inherent cost of that tile, right? So for each tile, I assigned it a cost, right? I had those red numbers on the board here that I just erased. So this is, so I'm going to take that cost plus the costs of the best tiles for the children of that tile. So I'm going to just illustrate that first. So, let's say I'm at this node here, and let's say I was to take, just the tile that covers only that node and that has a child X underneath it. I had a tile like that with a cost of 1 for that tile. Then if I was to use that particular green tile, then the child of that tile is this plus node here. And so what I want to do is figure out what is the best way to implement that plus node plus everything underneath it, and add that to the 1 cost of that of this green tile that I'm adding to my tile tree. Okay, and so so what I'm going to do is I'm going to sum over all of the children. So I'm going to say children of T. So if I was to use the tile T, rooted at the node N that I'm looking at, then that tile would cover some number of nodes, but then it would have some children coming out of it that are not covered by it, right? That still have to be implemented by other tiles. And for those, I'm going to use the min cost of that of each such child node, right? So in this case, if I choose the green tile, then my only child node is this plus node. So I'm going to look up in the min cost array, min cost of the plus, and that's going to tell me, what's the best way that I can implement the plus. What's the lowest cost that I can implement the plus with? Okay, and then I'm going to add that to 1, and that's going to be the cost if I choose the tile, this green tile for this particular node. Now, of course, when I waved my hands, I said, oh, we should choose this red tile, this bigger tile for this tree node. So the algorithm, it's going to consider all tiles that match the node. So it's going to consider that red one as well. And in this case, the red node is not going to have any children, right? Because it fully covers the subtree, all the way down, all the nodes. If there were more nodes underneath these ones, then it would have children below it, right? So in that case, for that red node, you would just have the inherent cost, that red tile, you would just have the inherent cost of the tile, and then there aren't any children, so this would be the 0. Okay, and just to drive the point home with one last example, For the root node here, again, we're going to consider various different tiles, but one tile that we consider is this kind of weird A tile. This red tile is a way of tiling this node. In that case, it has 3 children here, here, and here. And so for those, we would consider the min cost of tiling, this child node, and this child node. And we've already computed that earlier to mean to be, if you use these 3 red tiles, that's the lowest cost way of covering those subtrees of the overall tree. Okay. And so this is where the post order and the dynamic programming, the post order becomes important, right? Because the idea is that we need to have computed the min cost of every child node, before we start computing the node itself. So this is why we have to process the children first before we go and further up the tree. Okay, so if there's questions about this step, do ask. But I'm just going to close the loop here. Okay, and so we've figured out for each tile that we could use, which what the overall cost of the subtree would be. So now we just find the lowest cost tile to use. Right? So we're going to select tile of n is going to be the t such that tile cost of t is minimized. Okay, and then we need to update. So we've figured out tile of n, and we also need to compute min cost of n, but that's just so min cost of n is the tile cost of the tile that we chose. So tile cost of tile of n. Okay, so and that's the end of the loop here. And so if I run this algorithm on the entire tree, for every AST node, it's going to pick the best tile to implement that particular AST node. But some of those might not be actually used in a tiling, right? So to give an example here, for this node, it's going to pick the red tile because that's the best one. There was also the green tile that looks like this one. It doesn't pick that tile for this node. But for every node, it's going to have some tiles. So for example, for this plus node, the only way to tile it is going to be this way with just just that single operation. And here it's going to pick this one, and here it's going to pick this one. Like here, there's not many choices of how to implement these particular subtrees. The point is you're going to get this array tile of n for every node, but in the actual best tiling that you want to use, you might not actually use the values for specific nodes. If the tile for a higher up node covers those nodes, then you don't really look those up, right? So then there's a sort of a second pass to this algorithm where you start at the root node, you pick the best tile, the tile of n for the root node, you pick the best tile for that root node, and then you go and see the children of that tile, so here, here, and here, and sort of recursively pick the best one for each one. And again, if you pick the best one here being the red tile, then you look at the children of the red tile. You kind of skip over all these internal nodes. And similarly, you would skip over the internal nodes of this tile A. Okay, but the original DP, right, would still give you some tiles there, for this node and for this node, and and so on. But you just skip over those because at the root, you've already committed to this big tile for this entire subtree here. Okay. So again, questions, feel free to ask. But I think that's really all I have about this tiling algorithm. So I guess this is your last chance to ask questions about the tiling algorithm. And I'll stand over here so you can see it. I do have one more sort of code generation improvement to look at. Interestingly, it's going to be a very similar kind of a dynamic programming algorithm, but I think I'm getting ahead of myself there, right? That's the final solution. First, the problem, right? So I mentioned last week that for generating good code, we want instruction selection, instruction scheduling, and register allocation. And so, I've been focusing on instruction selection, and I got our example, I guess this example, I got that down to 8 instructions. So let's see if we can get it down even further. And to get it to get the code even shorter, I'm going to switch from instruction selection to register allocation. Right, those 8 instructions that we had, they were pretty good. They just weren't really using registers very well. So let's look at register allocation. Okay. So for register allocation, again, there's lots of algorithms. You could have like half a course, maybe a whole course, I don't know, just on register allocation. But there is one algorithm that is sort of simple, is very old, very well known. It should be covered here, and also it's an algorithm that's fairly easy to implement and gets you 90% of the way there. It gets you very far in terms of making good use of registers, right? Not as far as some more complicated algorithms, but already makes pretty good use of registers. Now, so let's look at that. Okay. I'll erase this part, but I'll leave my little tree down here. And I'm gonna say that we're gonna do optimal register allocation. Okay, which might seem surprising, given that I said that like all of these problems are NP hard, right, and interrelated, and you can't do anything optimally. You need heuristics, so why am I doing optimal register allocation? Well, it's going to be optimal register allocation for expression trees. Okay. So the idea is I'm going to find a register allocation that is not the best possible allocation of registers for an entire procedure, an entire program, but for a single tree, right? A single expression tree. So, I'm evaluating one arithmetic expression to get one result out of it. It's going to give me the best possible use of registers. Okay. What it doesn't do is, consider registers between different statements in a method, right? It only looks at one statement, one expression at a time, along with it, all of its sub-expressions, and it evaluates those, right? So if you have expression trees, then we can find the optimal allocation of registers. And actually now let me just take a step back. I guess I said I was done with tree tiling, right? But I had this dynamic programming algorithm, and this dynamic programming algorithm, like it also finds the lowest cost tiling of that AST. But the sort of the limitation is that it only works on trees, right? So if you're in general, the computations that your program requires can be represented more efficiently as a DAG, right? So if you have some sub-expressions, right, that are computed in multiple other expressions or in multiple parts of the program, let's say you have some variable and all over the place you're computing x plus 1, right? Or maybe you have some array index and you're accessing many arrays with that same array index. So you do that same array calculation, right? You multiply it by 4 and you add some constant 8 or whatever. If you're doing that computation many times, that's a sub-expression that you could actually evaluate only once and use that subtree as a subtree of many other trees. And that's when the trees become DAGs. They're directed acyclic graphs. They're no longer trees because some computations, some subtrees can be shared in different parts of the, I was going to say different parts of the tree, but that makes the tree not a tree anymore. Okay, so that's where the optimality breaks. Nevertheless, for expression trees, right? So if I have like a parse tree of some expression or an AST, I'm going to be able to find the best possible assignment of registers. Okay, so in this case, my the tree that I'm going to use as my expression tree is going to be this tree of tiles that I got from the tiling algorithm, right? So I'm doing instruction selection first. I'm figuring out what tiles to use, and then I'm going to figure out what registers to use within those tiles. You could also implement this algorithm without instruction selection first, just directly on an AST, but then you won't get the use of the complicated x86 instructions, right? So the algorithm, it just needs a tree. It doesn't matter whether it's the original AST or this tree of tiles, but of course the tree of tiles is going to select better instructions. And so, it's going to be a similar kind of dynamic programming thing. So what I'm going to do is for each node in the tree, I'm going to define a function, or I guess an array of R of n. And this is going to be the minimum number of registers so needed to evaluate the subtree at n. Okay, so it's a lot like this tiling algorithm where you're trying to compute the min cost of n. So here I'm trying to compute, I'm calling it R, but it's really the minimum number of registers to evaluate that node and everything, the entire subtree beneath that node. Okay, and so, how do I define this R of n or the number of registers? So, first let's consider nodes that have no children. So if n has no children, so then Rn is a constant. So I'm assuming that this node is either some tile or some operation. So, for example, if I have a tile that corresponds to the instruction, move EAX EBP plus 8, right? So this is like one of the B, C, and D tiles that I had in my example. Well, I'm not counting the stack pointer because, the stack pointer is always the stack pointer. But, this is an instruction that needs one register for its result. Right? I'm going to circle this EAX. So this needs one register. Right? The instruction other than the stack pointer, sorry, it's not the stack pointer, it's the frame pointer. But anyway, the same thing holds about the frame pointer, right? So other than the frame pointer, which we use everywhere, this instruction just uses that one register for its result. And the place where it gets interesting is for nodes in the tree that do have children, right? So let's look at node A, right? So node A has children B, C, and D, and those don't have any children, so their Rn is a constant. And in particular, for that example, B, C, and D kind of look the same. They're basically this kind of an instruction. So they each need one register. And now the trick is, assuming these nodes don't have any side effects, right? So they don't write to memory or, perform I/O or anything like that. Then the order in which I evaluate B, C, and D, doesn't make a difference, right? I can calculate these three sub-expressions in any order. And I'm going to take advantage of that. And sort of the general idea is that I want to evaluate the most complicated sub-expression first, right? So eval sort of the most register intensive child first. Okay, and so why is that? So let's say I pick the order B, C, D, right? The order that these sub-expressions are listed in. Let's say I decide to evaluate that them in that order. So example order B, C, D. Then what, how many registers do I need? Well, okay, I'm going to evaluate B first. So I need R of B registers to evaluate B. And now I've evaluated B, so I'm going to go on and evaluate C. Now, how many registers do I need to evaluate the subtree C? Well, okay, so here it's a trick question. It's going to be, R of C, R of C registers to evaluate the subtree C, but I've already evaluated B, and I need to remember its value somewhere. And, the idea is I don't want to be using the stack for that, because the whole point is to use registers instead. So when I go to evaluate the subtree at C, I need, all the registers that I need for C plus one register. So plus one registers for C. So to evaluate C, I need one register to remember what the value of B was, and then R of C registers to actually get the value of C. Okay, and then now you can probably do the sort of engineering induction, right? You generalize from there. I'm going to need R of D plus 2, registers for D. Right? So when I go to evaluate D, I need one register to remember what the value of B was, a second register to remember what the value of C was, and then R of D registers to evaluate D itself. And in each case, so let's say I'm evaluating C, I might need lots of registers for C itself, but once I've evaluated it, it squishes down into one register. So then when I go to evaluate D, I don't need the registers for C anymore. I just need one of these two registers here to remember that already computed value of C. Okay, so does that make sense? So depending on which order I am evaluating these in, I need to remember some number of earlier children of the node I'm looking at, so node A in this case. And so then I want to, so why do I want to evaluate the most register intensive ones first? Well, let me write down the sort of the general formula. Right, so R of A, I'm going to write it as R of A, right? But it's really R of any node n is going to be, well, it's going to be the maximum of these three values, of these three values, of RB, RC plus 1, and RD plus 2, right? So the maximum of these two values. So max. So I goes from, let's see, 1 to n, right? And I'm going to take, sorry, I need to, let's number the children starting from 0, right? So I goes from 0 to n minus 1, where n is the number of children, and then I'm going to take R of child I of node A plus I. Right? So in each case, the plus I is the registers that I need to remember the earlier sub-expression values, and then R of CI is the number of registers that I need to evaluate that particular child, that particular subtree. All right. So for my example, it would be the max of these three values. And, I mean, in this example, R of B, R of C, and R of D are all equal, but oftentimes they're not. And if they were not equal, what is the best strategy in terms of ordering the children to minimize this maximum value? Well, if you're going to have a third one that needs some number plus 2, and a first one that needs just some number, and your some numbers are different, then the way to order them is to do your biggest number first and add 0 to it, and then your smallest number last and add 2 to it, right? To sort of balance things out so that your overall maximum of those sums is as small as possible. So you're using as few registers as possible. Okay. Another way, a more concrete way of seeing it is if you have a complicated sub-expression and a simple sub-expression, you want to do the complicated sub-expression first, because then you're going to need one register to remember its value. But then for the simple sub-expression, you're going to have one fewer registers, because one register is already busy with the value of the complicated subexpression, but that's okay because for your simple subexpression, you need fewer registers than for the complicated subexpression. Right? So while you're computing the complicated things, you want to have as few simple things that you need to have lying around in your head, distracting you from the complicated things. So that's why you do the complicated expression first. Okay. So again, if there's questions, do ask, but that's the sort of the general intuition behind this. So, I have this kind of a pattern where the R of a node depends on the nodes of its children. And so the R values of the nodes, of its child nodes. So again, I need to compute all the R's, for all the nodes in the tree. So again, I can do some sort of bottom up. I'll just write it right. Bottom up dynamic programming, where I go in a post-order traversal. I compute the R value for each child node. Then I use this formula. Really, I should minimize over all the orders of the children, right? And minimizing these maxes. Okay. So to compute the R value for this node A, and so I do this DP. I'm not going to write out the whole algorithm because it has pretty much the same shape as the tiling algorithm that I just showed you. Right? You go over the nodes, and in each case you compute this R value. Using the R values of its child nodes. I guess, if you don't like dynamic programming, you could also implement this using memoization. It's, just a different, a different form of dynamic programming. You have a formula for R in terms of formulas for the children. And so you implement that recursively, and you use memoization to avoid recomputing things that you've already computed. So now I've, let's say I have computed R values for all of my nodes. And let me, I guess, write those down, right? So for node B, C, and D, I need an R value of 1. I need 1 register for each one. Those nodes, I'm going back to my tiling of the tree where nodes B, C, and D corresponded to this instruction, this tile with this one instruction. So they each need 1 register. And then for node A, I want the maximum of these 3 things. And if these guys are all, I want the maximum of 1 plus 1, or I want the maximum of 1 and 1 plus 1 and 1 plus 2. So the maximum of that is 3, right, which is 1 plus 2. So to evaluate the subtree rooted at A, I need 3 registers. Okay, so I've gone and figured out how many registers I need for each subtree. And now I need to use that information to actually generate code, right? So, now there's a key trick. So into the code gen function, for each tile, right, or for each AST node, we're going to pass as a parameter so pass a parameter to indicate that the first n registers are busy. Okay, so as I'm doing my traversal of the AST, or the traversal of the tile tree to generate code for each node, I'm always going to keep track of which registers or how many registers are holding values that I need, and how many registers, the remaining registers are free for computation. And then I'm going to use a convention that the result, spell result, right? So the result of the result of the node goes in register n+1. Okay, so this is the big change. I'll circle it. So all along, right, all last week and I guess the week before, and maybe even the week before that, I've always had this convention that when I generate code for a subexpression or for a subtree of the AST, the result of that subexpression, always ends up in register EAX. Okay, and now I'm changing that convention, and I'm saying when I call you to generate code for a subtree, I'm going to tell you, well, I've got 3 registers that are busy. Don't touch them. Okay, so you have to generate code that doesn't touch them, and now the rule is the result of your subexpression is not going to go in EAX. It's going to go into the 4th register, right? So I have to number the registers somehow, right? EAX, EBX, ECX, EDX, whatever, right? Order them somehow, but it's going to go in sort of the first not yet busy register. Okay, so when I first call CodeGen on A, I'm going to say nothing is busy because I'm just starting and there's no interesting values in registers yet. And so then A is going to go and generate code for B, C, and D in the order that I picked here, right? So in that best order for the to use the fewest registers. So I mean, for this example, the order doesn't matter. So let's say B first, then C, then D. And so we're going to generate code for B saying 0 registers are busy, right? So B is going to put its result in EAX. Maybe I'll, let's see, I've got a black marker, right? So nothing is busy. So B is going to put its result. Oh, and now I realize I wrote it really small, so you probably can't read it. But anyway, so B puts its result in the first register, which is EAX. Now I go to generate code for C, and I'm going to say 1 register is busy, right? Because 1 register is busy keeping track of the value of B. So register. So the result of subexpression C is going to go in EBX. And I mean, the point is that if, in this case, C doesn't have any children, but if C did have children in the tree, then when C goes to generate code for its children, it needs to tell them that, by the way, EAX is busy, right? So it's going to tell them that at least 1 register is busy. And maybe if C has already computed some intermediate results, then more than 1 register will be busy, right? So some registers are busy because B is using them, and so going down from A, we passed in this number here saying 1 register is busy when you're evaluating C. Then if C needs some registers while it's evaluating its children, it can add those to that number and tell the evaluation of its children, don't touch the first however many registers. Okay, but the point is the result of node C is going to go into EBX, and then similarly, by the time you go to generate code for D, you're going to say 2 registers are busy, holding the values of B and C, And so then, the CodeGen for D knows that it can't touch those two registers, and its value is going to go in ECX, right, in the third register. Okay, so this is where the register allocation happens, right? We're allocating the result of a particular subtree, right? And we're allocating it to a specific to a specific register here. Okay, so we're going to say result of B goes in EAX, result of C goes in EBX, result of D goes in ECX, and I suppose for completeness, the result of A is going to go into EAX, right? Because when I first called CodeGen on A, I had 0 registers busy. So the first register is going to get the result of A. So I guess one other way to understand this is to think of the registers as being a stack, but you're sort of statically keeping track of the stack pointer, right? So the registers get values at runtime, but at compile time you are deciding during the evaluation of each part of the sub-expression where the top of the stack of registers is, and generating code to put the computed values in that register, right? In the register specified by the top of the stack. Okay, so questions on that? All right. So, now we just have to kind of follow this strategy to go and generate code. And so basically, I'm going to go into A, and then that's going to recurse into B. And I want to evaluate B and put its value into register EAX. And so, for B, I have this tile here, that looks something like this. And so I'm going to put its result in EAX. And I'm going to dereference the frame pointer, and it was actually the frame pointer -4. So sorry, so it wasn't +8, it was -4 on our, on the AST that I had here that I erased, right? That I tiled and erased. So for that tile B, right, we get this instruction, and remember before. We said, okay, well, its result is in EAX, so now we push it onto the stack so that we can evaluate tile C. But the difference now is that tile C knows that it's not supposed to use EAX, it's supposed to use EBX. And so we're going to generate a move EBX, the frame pointer -8. And so that's going to be tile C, right? So let's say tile B, tile C. All right, and I think you see where this is going. So now we can go and generate code for tile D. We know that AX and EAX and EBX are busy, so we're putting the result in ECX, and so we'll do a move like this. Move into ECX, EVP -12, and this is for tile D. Okay, and now we just come back to tile A. And again, before, right, so the sort of the precondition for tile A was that we evaluated the children and their values were on the stack. So we had all those pop instructions to get their values off of the stack. In this case, tile A should look at these n values that it passed for evaluating or generating code to evaluate its children. So those specify which register to find the value of each of those children. So now you don't have to pop the children off the stack, and you can just generate that instruction that implements tile A, and that was that nasty that crazy x86 instruction, right? We take EAX plus EVX times 4 plus 8, and it doesn't even fit on a line, but it's an instruction, right? And so we store ECX, so we store the third child at this computed address, and this is the instruction that implements tile A. Okay, so I'll stand over here, but are there questions about how the code generation works, how we get these instructions from here? Basically, when we're generating code for each child, we're changing our convention of where you put the result, right? Put it in different registers each time, and the convention always is, put the result in register n+1, and while you're at it, don't touch the first n registers. Okay, and so for all of this, we have to make sure that we don't run out of registers, but we can do that during our computation of the R values, right? If we ever see a subexpression that needs more registers than we have available in our CPU, then we know that there is no way that we're going to evaluate that subexpression, so we have to spill some values to memory. We have to start using the actual stack for some subexpressions. So we kind of fall back to the old code generation strategy. Okay, so questions on that? So, so looking at the code, so last week we started off with an AST with the naive code generation strategy, and we generated code for it, and we had 17 instructions. We've gotten that down to 4 instructions. The instructions make good use of registers. They make good use of the complicated CISC instructions. And, for that particular AST, I don't know that there's, any better, shorter or faster code that you could implement that with, right? So for that particular AST, I think we've done as well as we can with some, pretty simple techniques. I know, it's been a long term. It's been a long, a big compiler that you've implemented. So I'm not asking you to implement these techniques, but hopefully you'll agree with me that they're not, really tricky, complicated algorithms. I think if you had a bit more time, they would be realistic things that you could realistically implement in your JUICE compiler, and you get like pretty good code, right? If you, in addition, if you throw a peephole optimizer on top of a code generator like this, it's going to generate very respectable code, right? Obviously, you can always do better. There's always okay. So I said finding the optimal code is very much NP hard. There's more complicated algorithms that are going to find you more optimal code, but these simple techniques will already lead to code that's very good. So I'll stand over to the side. So this is all I have in terms of register allocation, right? Again, to do more register allocation, you would consider expression DAGs and not just trees, and you would want to consider multiple statements so that evaluate multiple expressions and try to coordinate registers between those. Right here, we've just been assigning registers to the temporary results of subexpressions. We haven't been assigning registers to actual variables, right? So like variables in your JUICE program, right? Local variables. So to do more, to use more registers, you would need to consider variables as well, but that gets into more complicated algorithms, and then you get into the world where things start getting NP hard. With x86, you only have like 6 registers that you can use anyway. So, this is already going to be pretty close to the best you can do, right? Many sub-expressions will have around 6 possible temporary results. I guess you could do a little bit better, right? If your JUICE program has mostly simple expressions, you could put some local variables in registers. And obviously, if you had a CPU with more registers, then register allocation becomes even more important. Okay, so that's all I have on register allocation. It's all I have on code generation, and it's really all the material that I have for the course. So I just want to give you a chance to ask questions. We have a bit of time, so I guess this is, questions about this, but also questions about anything that has come up in the course. I'll give you a bit of time for that. All right. Okay, and I guess I announced it at the beginning, right? So the extension on the assignment 5 code, but not the document, right? Get the document in by Wednesday, but for the code you have till Sunday, and then the course evaluations. Okay, so I'm not seeing questions. I'll be on Piazza if you come up with questions later on. It's been definitely a weird term. Oh, okay. Sorry. All right. So I've got a question. All right, but it has been a weird term, but I've got a question. Casting between numbers. How do I cast between signed and unsigned? Okay. So is this a question about JUICE and Java specifically, or about sort of in general, right? So char 255 becomes short -1. So there was a question about this on Piazza, I think, and I'm trying to remember. Char 255 becomes short -1. Should char 255 become short -1? I thought there's narrowing conversions and widening conversions, and sort of the principle that Java uses is that you should think of well, okay, let me first go back to C. So C uses this principle that we're not really going to care too much about the numbers. We're going to view values as sequences of bits, right? And so there's sort of the normal thing that a cast does is you take these bits and you interpret them with a new type, and you don't really care too much about what the bits happen to mean under that new type. Sort of the underlying principle that Java is based on is that you don't want to be thinking about bits. And partly this is because Java was intended to be implemented on various different kinds of processors that might have different representations of different numbers, right? So in Java, the idea is that each of the Java types represents a range of numbers, right? So in this case, a char represents the range from 0 up to 2 to the 16 minus 1, right? Because chars in Java are 16-bit. And so, so the value of a char is a number within that range. And then if you're doing a widening conversion, sort of the idea is that you take that number, the actual number that your bits represent, and you try to represent the same number, right, the same integer, in the representation of the wider type. And I mean, in most cases, it happens to be that you use the same bits, possibly adds some 0 bits or some 1 bits. But the idea is you would keep the same. You want to maintain the same interpretation of those bits as an integer. And then widening conversions and narrowing conversions, right? So widening conversions are ones that take you from a type whose range of numbers is entirely contained in the wider range of numbers that you're converting to. So you can always preserve the numerical value of the original bits. Narrowing conversions go the opposite way. And so there the idea is, you're just going to cut off bits, right? Because you can't preserve the numerical value. And so that there was specifically a question about char and short. So now I see the example with char and short. And so the specific thing about, or the specific issue about char and short is that they have ranges that are neither a widening nor a narrowing, right? So the range of a char, so char goes from 0 to 2 to the 16 minus 1, and a short goes from negative 2 to the 15 up to positive 2 to the 15 minus 1. So, I mean, if I draw these on a number line, right, I have char looks like this and short looks like this, right, where this is 0. So this is char and this is short. So, neither, so they overlap here, but neither is entirely within each other. And so this is neither a narrowing nor a widening conversion. And so there was a question about that on Piazza. And the answer is this is, an ambiguity. This is not really specified in the second edition of the JavaSpec. But then the third edition clarified this and said that this is a widening and a narrowing conversion, right? Because it's either both or it's neither. And the rule that it says is that you first convert the char to an int, and then you convert it back to a short. So you do your widening conversion to an int, and then you do a narrowing conversion of the short, of the int back to the short, or the other way around, I guess. And so you would, in the case of converting a char to an int, you would 0 extend it. You would add 0 bits to make it 32 bits long, and then you would chop off the top 16 bits and treat the resulting bits as a short. In the case of converting from a short to an int, that widening, you want to preserve the value. So to preserve the value, if the value is negative, you need to sign extend it. So add 1 bits instead of adding 0 bits. And now you have an int, and now you can turn it back into a char by chopping off those 1 bits that you've added. So does that answer your question? I guess if you're thinking of chars and shorts as bits, well, they are 16-bit. They do require 16 bits to represent those ranges of values. So in this particular example, going between shorts and chars, you're going to have the same semantics as in C, where you're just taking those bits and reinterpreting them as signed or unsigned. Okay, not so much about. Professor Weddle was wondering if you would consider him an honorary PLer. Okay. So what? I'm not sure. I'm not sure what we actually what that actually means. So what's so PLer in what sense? So yeah, I think he does some work that overlaps with programming languages. Probably more than many other people who are sort of associated with programming languages. So in that sense, yes. Okay, I don't know. I think this is the kind of question that makes more sense in person than in a chat, right? I think we'd have to talk about this in person. Yeah, I don't know. I mean, I often chat with him about programming languages questions. So sure. All right. Any other questions? Okay. All right. 5, 4, 3, 2, 1. All right. So all right. So I'll wrap up. So yeah, I mean, it's been a weird term. I don't like being locked down. I'm sure none of you like it either. I think in terms of the course, lecture-wise, you don't have the full experience of seeing me in person. Hopefully, the YouTube was at least an okay substitute. But I think even more importantly, the group work is a lot harder. Trying to do that online, not being able to see your group mates in person. So I recognize that. For me, it's also annoying that I don't get to see your faces. Oftentimes I teach this course and then I see my former students in the hall, or maybe they come back to grad school, or they come back after they've been at their job for a while, and they come back to visit or whatever. And I really wish that I could see your faces so that I would recognize you in the hallways. Anyway, I think given all these challenges, at least so far, the way that the groups and the implementations and the compilers and the reports have been going, I think all of you have done a great job under the circumstances, and I hope that this whole situation doesn't last much longer, and that we go back to normal soon, and that soon the courses will be taught normally, and whatever all of you are doing will go back to normal, right? Again, whether I suppose whether that's grad school or going off to a job, or I suppose some of you might still be in third year, so more fun undergraduate courses. Either way, I hope things turn normal soon. And regardless of what happens, I wish you all the best in whatever you're doing in the future. And yeah, I mean, if I do have a chance to meet some of you in person, I would enjoy that. So we'll see. Hopefully, the future will allow for that. Okay, so thank you for attending the lectures. Those of you who attended them, and I know there's lots of you who are not attending them live, but attending them later on. So that's fine too. So thanks for being there. Thank you for all of your hard work. I know it's been hard work, and you've done a lot. And yeah, I mean it's still been fun, not quite as much fun as teaching it live, but it's still been a good experience for me. So I hope it has been, at least a bit for you as well. Okay, so thank you. See you again, and all the best for all your futures. Okay. Bye.